Everyone, welcome back to Math 256. This is Scott. Let's get started. What we are going to be doing today is the penultimate section that we will be covering in this course. That is section 6.3, delta functions and forcing. Alright, so what we are going to be doing now is pushing further into the topic of Laplace transforms and looking at some of the more interesting places where they can be used. And these will be, in some cases, places where none of the other techniques that we've learned for solving differential equations would apply. So, first off, let's look at some common tools for finding the inverse Laplace. So everything that we are going to be doing in the world of Laplace transforms is going to be intimately tied to finding an inverse Laplace transform. In particular, to solve differential equations using Laplace transforms, it is key that we be able to find the inverse Laplace transforms of whatever it is that we make. So first, let's look at what we could call translations. And in other words, shifts. All right. So the idea here is on the one side we'll have our function, and on the other side we'll have the Laplace transform of our function. And so here, what happens if we take our function and we multiply by e to the at? Well, over here, what that corresponds to is replace s by s minus a. So in other words, the Laplace transform of e to the at f of t, that corresponds to f of s minus a. And the reason for this, or actually, we should then push it a little further. So then the inverse Laplace transform of something where you see s minus a instead of just an s, that is the same as e to the at times f of t, where little f is the inverse Laplace transform of big F. So the reason for this. So let's think about the Laplace transform e to the at f of t. Well, by definition, what that's equal to is the integral from 0 to infinity. And then here, what have we got? We've got e to the negative st. And then instead of just f of t, we're going to have e to the at f of t, which we can then rewrite as 0 to infinity, the integral thereof. E, if I combine the two pieces here, and I pull out a negative and an negative and a t, then I'll have s minus a f of t dt, which is exactly the Laplace transform of f, but with s replaced by s minus a. Okay, so that's the reason why this is true. Now, how to use it? How to use this? So that's another question. So the idea here is rewrite. So in particular, we're talking about to find the inverse Laplace. So rewrite the given expression as a shifted formula from the table. And in particular, make it so that all s's are now written in the form s minus a for the same a. So put all s's, or put all s occurrences into the form s minus a. All right, let's see this in an easy example, and then we'll see this in a harder example. So sometimes this goes down pretty smooth, sometimes it is a little bit more involved. So let's see it in each case. So, example. F of s, capital F of s that is equal to s plus 1 over s minus 1 squared. Okay, so here we can see an s minus something, which is a good start. And in particular, s minus a is going to be s minus 1. All right, so we want everything to be in the form of s minus 1 instead of an s. So then, if we take the expression here, we want to be looking at an s minus 1 on the top instead of just an s, and an s minus 1 squared down here. Now this is clearly not equal to what I just wrote. So the way you can massage this is basically put an s minus 1 plus 1 and then plus the original. So s becomes s minus 1 plus 1, and then that in turn becomes just s minus 1 plus 2 over s minus 1 squared, which I would then break up into two pieces. I'd have s minus 1 over s minus 1 squared plus 2 over s minus 1 squared, which just algebraically, not doing any kind of calculus, would just simplify to become 1 over s minus 1 plus 2 over s minus 1 squared. And each of these is in the format of one of the pieces of our table of Laplace transforms, and in particular, the first one fits the format for the Laplace transform of merely a constant function, or, in other words, also an e to the t, e to the at. So constant function times e to the at, or just e to the at. This is basically just 1 times e to the 1t, and this is plus 2 times t e to the 1t. So in other words, just e to the t plus 2t e to the t off of our table. Now, that's kind of this is sort of the best case scenario where you don't have to do anything too exotic in your algebra. But sometimes you do have to do something a little bit more off the beaten path, such as this. So a common trick that we may need to do is to complete the square. Completing the square. And this will happen in the denominator. Oops, denominator. And in particular, when we would have to do this is when we have an expression that can't be factored. When we have a quadratic expression in the denominator that we can't factor, we rewrite it as a completed square so that it fits the formula for a shifted sine or cosine Laplace transform. So just an example of what this might look like would be something like this. Let's say f of s is equal to s minus 3 over s squared plus 4s plus 8. Now the s squared plus 4s plus 8 is not itself in any kind of usable form. And in particular, it can't be factored. So our previous technique of factoring it and using partial fractions is off the table. It also is not of the approved format of s squared plus k squared, or s squared minus k squared for that matter. And so we're still kind of stuck. But if we rewrite it as a completed square, and in particular, to remember how this works, so s squared plus 4s plus 8. So basically what you want to do is make the perfect square that would match the first two terms of this, and then you would add or subtract whatever was necessary to make it fit whatever you started with. So if you think about this, so the usual way here that this would go is if the coefficient here is a 1, and we call this the b, then you would take b divided by 2, so b equals 4, then you'd say b divided by 2 is equal to 2, and so then you'd say b divided by 2 squared equals 4. So then what you have is s squared plus 4s plus 4 here. We wanted it to look like this because we can recognize this. This is a perfect square, but it doesn't match the original. So then, we say then plus 4 more to make it match the original. Or you could Also think of it as adding 4 and subtracting 4 to make that line up. And the reason why this works, the reason for this this process, you take the b coefficient and divide it by 2, you square it, and that's what the third term has to be. It's because if we have a perfect square, s squared plus or sorry, I should say s plus something plus h squared, that's going to equal s squared plus 2sh plus h squared. And so then if we have s squared plus bs plus c, then b is equal to 2s. So then s, sorry, 2h I should say. So then h is equal to b over 2. And then this would be b over 2 squared. So again, this is just meant to be a reminder of a process that hopefully you've already seen at some point in your lives, maybe not in this exact format, but somehow. And so if you have not, you may need to do a little extra research on the process of completing the square. If you've never seen anything like this before, this will be a very hard line of reasoning to follow, perhaps. But in any case, it's a process you probably have done at least once before, either as an independent algebraic topic or also in calculus when it comes to doing certain kinds of integrals by the table of integrals. In any case, so once we have found the perfect square that the denominator of this is in fact equal to, we would want to rewrite it as such. So what we have here is a reformulation of the denominator so that the first 3 terms are a clear perfect square. So then what do we have? We have s minus 3 over s plus 2 squared plus 4. All right, so that's starting to look more like it. So that's starting to look more in the lines of a trigonometric expression. But one thing that's important here is that all the occurrences of s must be replaced by s plus 2. So here our a is going to be played by a negative 2. So I need to rewrite this as s plus 2 minus 2 minus 3, because I can't have any regular s's sitting around. They must all be in the form of an s plus a or s plus 2. Okay, so then what do we have? We have s plus 2 over s plus 2 squared plus 4 minus 5 times something over s plus 2 squared plus 4. And then for this one, we are now looking at, so this one is going to be a shifted cosine with k equals 2, a equals negative 2. This other one is going to be a shifted quotes here, shifted cosine. And this other one's going to be a shifted sine with k equals 2 again, a equals negative 2, but it doesn't quite fit yet. Up here, we're supposed to have a k. So this should be a k. So this is supposed to be a k. So it's supposed to be a 2. So then I balance the books by making it 5 divided by 2. So it's all a matter of robbing Peter to pay Paul here. We had to change this to an s plus 2, so we did s plus 2 minus 2 minus 3, and then separated the terms out. And then this was supposed to be a 2 on the top, so we put also a 2 on the bottom. So now, finally, we are ready to take the inverse Laplace transform of this expression, and we finally have it just the way we want it. We have a known a known Laplace transform here, except there's an s plus 2 where there's ordinarily supposed to be an s. And we have a known one here, again though, with an s plus 2 where there was ordinarily supposed to be an s. So what's this mean? This means we're going to have e to the negative 2t cosine 2t minus 5 halves sine, e to the negative 2t sine 2t. So that's what expressions like this end up looking like. Now when we can factor the quadratic in the bottom, we typically will. We won't complete the square, although technically, actually, you could complete the square, and then what you would get would be based on cosh and sinh, but that's not really something that we are going to look into right now. I'm just saying, just putting it out there, that this general approach would actually also work even if the expression that you saw did not did not need to have the square in the denominator completed, even if it could have just been factored as we've usually seen. It can still be done in this same manner, and then instead of cosine and sine, we would be talking about hyperbolic cosine and hyperbolic sine. But I'll let you explore that on your own. So when the quadratic can be factored, that's typically a case where we'll use the quadratic, where we'll use partial fractions. When the denominator can be factored, we usually use partial fractions. And we've seen enough of those types of examples, I think, to put it off for now. Now, what this means, though, is that sometimes you do have a choice when you are doing your Laplace transforms, and your answers may look different depending on the method you use. Depending on the methods you use. You can get different seeming functions when finding the inverse Laplace. But they should all agree for all t greater than or equal to 0. All such functions should be equal for all t greater than or equal to 0. And the only exception might be except possibly at a couple of discrete discrete points. But we won't belabor that. It's a matter for a little bit more in-depth analysis than we will typically do. All right, so now that we've got these techniques a little bit nailed down, let's see one of the places where we will make great use of them, and that is with the Dirac delta function. All right. So this is related to the unit step function, but it's not actually a function, hence the scare quotes. It is what's called a generalized function. The Dirac delta function, Dirac delta, which what is right? Delta of t. And it's the delta that swoops around this way. Delta of t is what's called a generalized function. Which again, it's not really much of our concern defining what this exactly means. That's it's a little bit more involved in the weeds of mathematical definitions than we're planning on getting here. But here's what we use it for. That we use as the derivative of the otherwise undifferentiable unit step function. U of t. And actually just remind you what U of t meant. U of t is the function that is 0 when t is less than 0, and it's 1 when t is greater than or equal to 0. So u has the value of 0 until it has the value of 1. So it is constant everywhere except at one point, and at that one point it is discontinuous, it jumps. So those of you who remember your training in Calc 1 will know that if a function is not continuous, then don't even talk to me about it being differentiable. But here we are actually we're using a substitute expression for the derivative of the u of t, and it represents essentially the rate of change that executes this kind of a little jump. And it's not an actual function, but it's what's called a general function, or sorry, a generalized function. And so then, what that means is, so that well here I'll explain all the things it means right now. So we use delta of t minus a Actually, I feel dirty writing derivative. Why don't you put some quotes on it? Quotes, quotes, quotes. For u sub a of t, and this function represents the delta function basically represents applying a unit of instantaneous sudden impulse. The use of delta to represent situations in which a concentrated impulse is applied. And the kinds of things that this could represent would be, for example, so e.g. collisions. So a collision is nothing until it's a lot. It's not really very well modeled by a continuous process. It's a sudden process, an instant process. So collisions, or another thing would be switches in electrical circuits. Electrical. In electrical circuits. Okay, well, if this new generalized function, as it were, is going to find itself in chapter 6, it had better have something to do with Laplace transforms, or in particular, we'd better be able to find the Laplace transform of it. So let's think about that. So the Laplace transform of delta t. Well, let's think about this. So the Laplace transform of the derivative of the unit step function. Well, we know how to take the Laplace transform of a derivative. That is just equal to s times the Laplace transform of the function minus the initial value of the function. Now here, this equals 0, so this is just going to equal s times the Laplace transform of the unit step function. And if you remember, the Laplace transform of the unit step function is just going to equal 1 over s. And so this is just going to equal 1. Or more generally, the Laplace transform of the derivative with respect to t of the, so now let's go delta t minus a. So this is going to be u sub a of t, which is going to be then again s times the Laplace transform of u sub a of t minus u of 0. And this is going to equal then just s times e to the minus as over s, which is then just going to equal e to the minus as. So there we have it. So there we have the Laplace transforms of the delta functions. Now, what are we ever going to use these for? Well, one place where we might use them is in a spring system, in particular a spring system in which we will be applying a force in a sudden way. So let's look at some applications here. Now we've seen the spring systems before, but here we are going to look at them in particular with an eye to what is actually in play here. So, and we want to compare them with something that actually turns out to be more similar than it looks. So mechanical systems and electrical circuits. So starting with springs, which I think are something we can kind of get our heads around relatively straightforwardly in many cases anyway. We can have a little spring, and let's say it has the spring constant of k. And then attached to that spring, there is a mass of m, and then that mass is attached to what we call a dash pot, which is actually just a sort of a catch-all representation of the friction or anything of that sort that is being applied to the system in order to take some of the energy out of it. So this is a spring with constant k, mass m, and then a dash pot, i.e. friction, with a coefficient of c. Then, if x represents the displacement from the equilibrium position, and there's an external force called F of t, then our equation would be mx double prime plus cx prime plus kx equals F of t. Now, that's one system that we will be looking at some examples of. But there's another system which may seem very different at first, but as you'll see, is actually much more intimately related than first glance would suggest. And that's the Rlc Electrical Circuit. All right, so here's the setup. for this. Let's say what we've got right over here. Right over here, we'll call this E. And this will be the source. So it's going to be a source of an electromotive force. And down here, we're going to have a resistor. Just write a little zigzag. This is a resistor. With resistance R. And then up here, we're going to have an inductor. And it's going to have inductance L. That's the R, that's the L of our RLC circuit. And then what we're going to have next up here is going to be a capacitor. With capacitance C. And then what happens next is we are going to have a switch. So we're going to have a switch right here. And the switch can be in one of two positions. It can be open as you see it here, or it can be closed. And as long as it's open, then it's cutting off basically the source here from doing its magic into the circuit. But as soon as it closes, then all of a sudden the circuit fires up, and all the electrical things that you can study in a physics class will happen. Now, in particular, one of the things that you will study in a physics class would be Kirchhoff's laws, and it's not our job here to go through all of those laws or their ramifications, but just in as much as they apply to us. And in particular, what is going to be of great use to us is specifically Kirchhoff's second law. So Kirchhoff's second law. In particular, it implies that L times Q double prime of T. So Kirchhoff's second law has to do with the overall change in voltage over the course of all the steps along the way. But as far as we're concerned, what we need to know is that it implies basically this differential equation: L Q double prime of T plus R Q prime of T plus 1 over C Q of T is equal to E of T. And just so we know what everything stands for here, where Q of T is the charge. Charge, and that's in coulombs. So charge, just sort of physically speaking, just represents the preponderance of protons or electrons, basically. E of T is what's called the electromotive force. Or we could also call it the impressed voltage. Note, though, that the charge is not actually one of the things that we are typically going to be focusing on when we're talking about these electrical circuits. Rather than the charge, what we want is the rate of change of the charge, which is the flow. In other words, the current. So that is the derivative. So Q prime of t is equal to I of t, and that is the current. And the units for that would be amperes. So we can rewrite the equation. L I prime of t plus R I of t plus 1 over c, and now we have just so we still have q. We can't really have like what would we call it, the zeroth derivative. It's a little odd. Is equal to e of t, or this is often also written as this. So so here, actually, I guess this is the antiderivative is really what it is. Sorry, this is the antiderivative of the current. So, or this can also be written as this in this format, where we've now replaced this q of t, which is not which is different from the I of t. It's the antiderivative of it, by what the fundamental theorem of calculus would say would be an equivalent expression, and in particular would be the integral from 0 to t of I of tau. D tau, and that equals e of t. And this is what's called the integral differential equation. For the circuit. And that, again, is a thing that people sometimes use, but it's well beyond our comfort zone. We don't like to have an equation that involves integrals and derivatives together. Hence the name integral differential. So if we just differentiate both sides of this, we'll be great. So differentiate both sides to get rid of that integral. And that'll give us the form that we'll be making most use of. Differentiate to eliminate the integral. And that gives us L I double prime of t plus R I prime of t plus now just 1 over c I of t. And that equals e prime of t. All right, well, that's all well and good. Uh, and in particular, actually, now that we have gotten through the nitty-gritty of it and gotten to this point, we look at this equation, we look at this equation, and we look back at the spring equation, and we realize that the letters are different, but those are actually all three the same basic equation. What's it all mean? What is nature trying to tell us? So, let's explore that. Notice Notice that the circuit equations, I guess we have two, the one we started with and the one we ended with. The circuit equations have the same form as the spring equations, or spring equation. So if we put them all side by side, you can see. So for the spring, what we had was mx double prime plus c x prime plus kx equals f of t. For the charge, what we had was L Q double prime plus R Q plus 1 over C, I'm sorry, Q prime, plus 1 over C Q is equal to E of T. And then for current, what we had was the same thing as far as the L, the R, and the 1 over C, but with I's now. So L, I double prime, R, I prime, plus 1 over C, I, and that equals E prime of T. And so the fact that these three equations have all the exact same format gives rise to what is called the electrical mechanical analogy, or also sometimes things like this are referred to by the name impedance analogy. So this gives us the quote unquote electrical for some reason I'm having a hard time writing the word electrical. Yeah. Sometimes differential equations are easier than spelling. Electrical, mechanical, analogy. Or sometimes the impedance analogy. And in particular, we can line things up and look at what is analogous to what. So from the spring, from the charge, and from the current. All right, so x of t, which is position, which is the thing that we're primarily measuring, corresponds in the charge equation with the thing that we're primarily measuring, which is the charge, hence the name. So Q of t, the charge, And then in the current, that represents I of t, which is the current. All right, well, the next line of our analogy, F of t. So this is the external force. So that's what is going to be imparting some motion to our spring. So here, this corresponds to E of t, which is the electromotive force. Which also corresponds to E prime of t on the current side, which is just the derivative of the electromotive force. By the way, EMF is another name for the electromotive force, which is the over here E prime, which is the derivative of the electromotive force. Okay, makes sense. I think the external force of the one corresponds to the external force from the other. Seems legit. And now we get to the part that I personally like the best. I find the most appeal in it, and that is connecting some of the pieces of the spring equation. So the spring constant, the mass, and the dash pot, connecting those with the parts of the circuit. Because for me at least, it's a lot easier to visualize what's going on with the spring than it is to visualize what's going on in an inductor or in a capacitor or in a resistor. And I always find this analogy particularly useful when it comes to trying to understand what exactly the different pieces of the circuit are doing. So, for example, mass, you'll see, corresponds with L, so the inductance. Okay, so induction is not something that I understand very well, but mass is something that I've been around my whole life. And so this tells me that when we're talking about a spring, mass is the thing that gives the little bob its inertia. So it's what keeps it from getting going, and then once it's going, it's what keeps it going. So then inductance plays the same role for both charge and for current. Good to know. Now C, which basically schematically we represent with a dash pot, but which is really friction. Make no mistake about it. Friction is what the C is there for. So that corresponds to the resistance. Makes sense. Makes sense to me. I don't know exactly what a resistor is doing, but the idea that it is analogous to friction is very appealing. And then K. The spring constant. So the spring constant basically tells you how springy the spring is. A higher spring constant means a spring that's stiffer, and a lower spring constant means a spring that is less stiff. So we can call this even the stiffness, just to help us understand the role it plays. And what this corresponds with is 1 over C, or in other words, reciprocal capacitance. And this will, of course, still be the same. Same for all these, because they all are in the same position in the equation. Okay, well, that's interesting. But does it have any more use than helping me to understand the complicated goings-on in a circuit? Actually, it turns out it has been quite useful in a lot of cases. In particular, it's an interesting historical fact. that when they were designing the first nuclear reactors for power plants, they actually, since they had to have a very high stakes mechanical system going on there with actual particles going at high energy, hitting each other, doing their thing, they actually created a simulation of it by making an electrical circuit. So this is actually what's called an analog computer, and it actually is an electric computer, not electronic, but electric computer, where a circuit is designed in such a way that the mechanical electrical analogy is respected, and some actual mechanical system is completely mirrored by the various parts of the circuit. So then you can measure position by measuring the current of the circuit at different times. So this was done, for example, in modeling the early nuclear reactors, and actually it was continued. This process was continued for a lot of other things, including power generators like hydroelectric dams, things like that, throughout the 20th century. It wasn't really until regular computers, the electronic computers, started to become a lot more usable, that they largely took the place of the analog computers that are based on actually just setting up this analogy in all of its glory. Anyway, let's look at an example here. This would be an example for a spring to start with. Springs are a little bit easier, so we'll get started with that. So we'll just say mass equals 1. Start with C equals 0. We'll think about what that means in a second. K equals 4. And we'll say f of t is equal to sine 3t. All right, well, C in the spring represents the friction. So there is no friction here. So this is essentially undamped, but it is forced. And we'll just give it an initial condition of x of 0 equals x prime of 0, which equals 0. So we'll just say it starts off at equilibrium and at rest. All right, then, what's the equation going to look like? It's m x double prime, so it's going to be 1 times x double prime plus 4 is equal to sine 3t. So now we can take the Laplace transform of both sides, and let's just see what happens. So here what we get is s squared times capital X. Capital X stands for the Laplace transform of little x, minus s times, s times x of 0 count down the s's, up the derivatives, minus x double prime of 0, x prime of 0, plus 4x. Sorry, that's what was distracting me, was something felt wrong, was that part missing right there. Okay, and then plus 4x is equal to, and then right here, what are we going to have? So this is k equals 3 sine. So sine goes with k on top, and then it's s squared plus k squared plus, because t for trigonometry. And then over here, what do we have? We have capital X times s squared plus 4. Oops, equals, okay, we have a number 4, 3. Is equal to 3 over s squared plus 9, meaning capital X is equal to 3 over s squared plus 9, s squared plus 4. Alright, well, so be it. Then we're going to want some partial fractions here. So for the partial fractions, we are going to, we're going to say 3 over s squared plus 9, s squared plus 4 is going to equal mystery. So we have s squared plus 9 for the first term, s squared plus 4 for the second term. And on the top here, this has to be as plus b, and this has to be cs plus d. Now you multiply everything out, or multiply everything by the common denominator to cancel it all out. You just a 3 on this side. As plus b times s squared plus 4 plus cs plus d times s squared plus 9. And so then you'll want to multiply it all out and or do whatever you would want to do here. I'm going to just go ahead and multiply it all out. So I'll have as to the third plus 4as plus bs squared plus 4b. And then it's going to look very similar over here. So cs to the third plus 9cs plus ds squared plus 9d. That all just equals 3. Now I'll just take the pieces each in turn. So all the s cubed will be 0 on one side, a plus c. All the s squared, 0 on one side, b plus d. All the s's, 0 on one side, 4a plus 9c, and then constants. Looks like we've got 4b plus 9d on the one side, 3 on the other. Alright, so then you put all the pieces together and you see, okay, a equals negative c, negative c. Also b equals negative d. So then we put those in and we have 0 equals negative 4c plus 9c. So then that gives us c equals 0. And so that means a equals 0 as well. And then by the same kind of algebra, we replace the b over here by negative d, so it's going to be negative 4d plus 9d. So that's going to be 3 equals 5d. So then d equals 3 over 5, which means b equals negative 3 over 5. And so then that gives us that capital X is equal to, let's see, what was b? B was the constant, so I'll put negative 3 over 5 times s squared plus, 1 over s squared plus 9 plus positive 3 over 5 times 1 over s squared plus 4 . But then neither of these is quite in the approved format for a Laplace transform of sine or cosine. In particular, here we have a k up here, so we're looking at a sine, but there need to be 3's on the top. So in particular, if I want to rearrange this, I can just move the 3 up there on this one. And up here, sorry, this one needs to have a 2 up top. So needs to have a 2. So then to rob Peter to pay Paul, I will put an extra factor of 2 down there to make that 10 now. And so then that means finally that I have something that I can take the inverse Laplace transform of, because it now fits the profile of sines. So here what we have is negative 1/5 sine 3t. And what we have right here is plus 3/10 sine 2t. And we can see actually that from the format of this, we are going to have beats in this case, because we have two sinusoidal functions of different periods, and so they will be interfering with each other. All right, so let's now take another example of a spring, only this time we will put some friction in there. So the last one didn't have any friction, so it was an undamped spring. So here we will start allowing some dampening. This is going to be another spring. This time m equals 1, c equals 6, k equals 34, f of t equals 30, sine 2t. And for initial conditions, we'll just start it the same way. X of 0 equals x prime of 0 equals 0. So starting at rest at equilibrium, but it's got this forcing function, but it's also got a dampening function on it. All right, so going to the equation, we have mass is 1, so it's going to be just 1 times x double prime plus 6x prime plus 34x is equal to 30 sine 2t. So if I take the Laplace transform, that's going to give me s squared x minus s x of 0 minus x prime of 0 plus 6sx minus x of 0 plus 34x equals, over here we're going to have 30 times, and it's sine, so it's going to be k up here, and s squared plus 4 down there. All right, so these are equal to 0, 0, and 0 by our initial conditions. So what we have then is s squared plus 6s plus 34, all as a factor of our x. And or equals 30 times 2 over s squared plus 4. So then what's that mean? That means x equals, let's go ahead and multiply those together, 60 on the top. We're going to have s squared plus 6s plus 34 as one factor on the bottom. And over here we'll have s squared plus 4 as the other. All right, well, looks like we got some more partial fractions to do here. So 60 over s squared plus 6s, 6s plus 34. That's not factorable, so we'll deal with that later. S squared plus 4 is going to equal to mystery as plus b, s squared plus 6s plus 34 plus cs plus d, s squared plus 4. And so now we can again take it to the next step, which is multiply everything by the denominators, and we're going to get as plus b, s squared plus 6s plus 34 plus cs plus d times s squared plus 4. And actually at this point, it's easier sometimes not to multiply it all out, but to look for the pieces that are going to have the degree that you want. So for the s cubed term, we're going to have 0. It's going to be a on the right, and there's going to be c on the right. And that's going to be it. There's no other way of making an s cubed out of these. For the s squared, we can see that there's going to be it's going to be one from 6as, sorry, 0 on the left, 6a plus b, and then over here, what are we going to have? We're going to have plus d. Just s. Looks like we're going to have 0 equals 34a plus 6b plus 4d. Sorry, 4c, I mean. And then for constant, looks like we're going to have 34b. So we're going to have constant. So 60 equals 34b plus 4d. Okay, well, then if I want to solve this, I could go step by step, and it would eventually get me there. It'd be a hassle, though. In fact, more of a hassle than I want. So, if you remember your linear algebra training, you can figure out how to make your technology do your bidding for you on this. The important thing is you can set it up as a matrix. With A, B, C, and D as the variables. And each of these equations will translate into one row. So we're going to have A, B, C, and D columns. And so we'll have 1A, 0B, 1C, 0D equals 0. Over here, we're going to have 6A, 1B, 0C, 1D equals 0. Over here, we're going to have 34A, 6B, 4C, 0D equals 0. And over here, we're going to have 0A, 34B, 0C, 4D equals 60. And then if you row reduce this, or invert it, or do whatever you're going to do, then you would get 6, 1, 0, 1, 34, 6, 4, 0, 0, 34, reduce down, and it would produce 1, 0, 0, 0, negative 10 over 29, 0, 1, 0, 0, oops, 0, 50 over 29, 0, 0, 1, 0, 10 over 29, and then finally 0, 0, 0, 1, and that's going to be another 10 over 29. Alright, I've just realized something. These numbers, they came from me entering something slightly different from this in the calculator. I originally set this up with AS plus B over the S squared plus 4. So these are not the correct coefficients, or the correct solutions. It should actually be 10 over 29, 10 over 29, and then negative 10 over 29, and 50 over 29. So basically I interchanged, when I was doing it this time, I interchanged what was A with what was C, and what was B with what was D. So, so ignore these numbers. These are the real ones. Okay, so what do we do with them? Well, we have so we have then that capital X can be partially fractions decomposed into 10 over 29 times, basically you can just write it as S plus 1 over S squared plus 6S plus 34. We'll deal with that in a second. As you can see, since we can't factor it, we're going to have to complete the square. And then for the other one, well, let's see what's the best way of writing it. We can go just with negative 10 over 29 times S over S squared plus 4. And then we can do plus 50 over 29 times 1 over S squared plus 4. And now we can start getting things into a more preferred format. Alright, so first off, we can note that we may prefer to have a 2 over here, because k equals 2. In this case, this is looking very trigonometric, and with k equals 2, so we'll want 2 over there. So this one, we might just go ahead and make it a 2, and a 25 like that. Okay. Now for here, if we're going to be completing the square, we have to ask ourselves what perfect square starts with S squared plus 6S. Well, those of you who are very on point with your polynomials may already remember what perfect square it was that starts that way. But if not, what you can always do is just say b equals 6, which implies that b over 2 is equal to 3, and then that implies that b over 2 squared is equal to 9. So then this is going to be s squared plus 6s plus 9. And then to make it balance out, we can figure out if you subtract the 9 from the 34, or you can make it 9 plus 9 minus 9 plus 34. So then that's going to be s squared plus 6s plus 9 plus, looks like 25. And this is exactly, of course, s plus 3, I should say, all squared. So then what's that make our x? That makes it 10 over 29 times s plus 1 over s plus 3 squared plus 25. So note then that means k equals 5 here, and a equals negative 3. Good to know. 10 over 29, s over s squared plus 4 plus 25 over 29 times 2 over s squared plus 4. So I just need this to be written more consistently with s plus 3's everywhere. So what I just need to do is rewrite this as s plus 3. And I can see it would be minus 2. S plus 3 squared plus 25. 10 over 29. S over s squared plus 4. 25 over 29. 2 over s squared plus 4. And what do we have now? Looks like if I break it up into two pieces, got 10 over 29, s plus 3 over s plus 3 squared plus 25. And what's the next part going to be? It's going to be minus 20 over 29. And then I can, what I can do here is in flow, I'll adjust it a little bit. So s plus 3 squared plus 25. Now I want this to be a k. So I want this to be a 5, so I need to balance it by dividing by 5, which will cancel a little bit here, make a 4. Alright, and then what do I have? 10 over 29. All the rest of these were already good as is. It's an S, not a 5. Make sure when you're writing your math, you have a distinct way of writing S's versus 5's to avoid that kind of confusion. 25 over 29. See, I put a little, I make my 5's very distinctly 5-like to distinguish them from my S's. Okay, so now I think we're good. So we can figure out the little x, which is the overall solution. So little x then, it's going to be 10 over 29 times. So this matches exactly the formula for cosine, except that every s has become an s plus 3. That means e to the negative 3t cosine 5t minus 4 over 29. This matches the sign, except once again, where there was supposed to be an s, there's an s plus 5. So it's going to be e to the minus 3t sine 5t. Here, this is an s, so this matches cosine, which makes it 10 over 29 cosine 2t. And then right here, what we have is a 25 over 29, and this matches sine, so it's sine 2t. Now note, by the way, that the first two terms here are exponentially decaying, and the other two are not. So quick note. The first two terms exponentially while the second two don't. We call first two terms x tr of t and it's called the transient solution. We call the other two terms XSP of t, the steady periodic solution. Oops. And hopefully the names make sense. Transient means going through. It is a solution that it only exists for a brief period of time. And it, by the way, represents the natural frequency of the spring. And it's the frequency of the forcing function that actually ends up being the steady periodic solution for the whole thing. All right, well, that was a spring, the second spring that we saw. Now let's finally look at a circuit. So here's how circuit problems will look for us. So in a class on circuits, you'll get many more variations on this, but we are simple folk, and we'll just do these in a very specific format. So here's what we will typically have for our circuits. We'll typically use this format, Li double prime plus Ri prime plus 1 over Ci equals E prime of t. But we won't usually have I prime of 0 given to us, and so we'll need to solve the equation for it. So we won't usually have I prime of 0 given. And we need to solve for it in the equation L I prime of 0 plus R I of 0 plus 1 over C Q of 0 equals E of 0. And all the pieces here are I of 0 is the initial charge, initial current. Q, of course, is the initial charge. And E of 0 represents the initial voltage. And E of t will often be a piecewise function, where open switches produce an impressed voltage of 0, and closed switches produce a non-zero impressed voltage. All right, let's just see what this looks like as an example. All right, for example, let's just say we have a resistance of 110 ohms. We have an inductance of 1 Henry. We have a capacitance of 0.001 farads, and it is initially passive. With initial voltage supplied by a 90-volt battery. So in other words, E of 0 equals 90 volts. And initially passive here means Q of 0 equals 0, no charge. I of 0 equals 0, no current. Okay, well then, so we have the LRC, so we have the 1 times I prime of 0 plus 110 times I of 0 plus 1 over 0.001 times 0 is equal to 90. Well, if this equals 0 and this equals 0, then that means I prime of 0 equals 90. Alright, so that's how you typically will set these things up. And now, let's say that E of t is given by the following function. So given by the following. Alright. At t equals 0, the switch is closed. And there is an EMF, that's electromotive force or impressed voltage, of 90 volts. At t equals 1, oops, the switch is opened. And the EMF becomes 0. Alright, well then what that means is E of t is equal to the piecewise function 90, and that's when 0 less than or equal to t less than or equal to 1. And then 0 when t is greater than 1. Alright, well, it will be useful frequently to reformulate these things in terms of the unit step function. So E of t is equal to 90 times 1 minus the unit step function of t. And just to confirm that this works, that will be 0 until t equals 1, at which point it'll be 1. So this will be 90 until t equals 1, at which point it'll be 0. Perfect. Okay, well then, what's e prime of t? Well, e prime of t would then be negative 90 times the delta function of t minus 1. And also a reminder, so initial conditions here were I of 0 equals 0, I prime of 0 we found was 90. Okay, well then, what's that going to mean? That means I double prime plus 110 I prime plus 0 divided by 0.001 times I is equal to negative 90 delta t minus 1. So this is now the differential equation that we use for our circuits. And so then, what's that going to mean? Well, first off, we can't deal with that. So let's go ahead and rewrite that as 1000 I. Okay, so now, if we put this into the Laplace transform, that's going to be s squared times capital I minus s times I of 0 minus I prime of 0 plus 110 s capital I minus s, I guess 110 times all this, sorry, minus just I of 0 plus 1000 capital I, and it's equal to negative 90. And if you remember how the Laplace transform of the delta function works, it's just going to be e to the negative s. All right, so this is going to be just 0. This equals 90. This equals 0. So what have we got here? Got s squared I minus 90 plus 110 si plus 1000 I equals negative 90 e to the negative s, which we can move the 90 over, and so we'll have I times s squared plus 110s plus 1000 is equal to 90 minus 90 e to the negative s, which then means that we can rewrite this as I equals, and the most convenient way typically of writing this will be like this. So 1 minus e to the negative s times 90 divided by s squared plus 110s plus 1000. But this can factor. Into 90 over s plus 100 times s plus 10. And so now we will just proceed with a little bit of the old partial fractions. And as far as the partial fractions is concerned, what we're going to be doing is taking just this part here on its own, and we'll deal with the 1 minus e to the negative s all in good time. Alright, so just this part right here, let's try to decompose that. So that's going to be the 90 over the s plus 100 times s plus 10, and that's equal to a over the first, so, and then b over the second. Standard issue, partial fractions here. We also could have pulled the 90 out to the front and done it with just a 1 there. It doesn't really matter what we do. It will all come out the same in the end. The important thing is we are not focusing on this part just yet. First, we're just going to deal with this part. Okay, so then, what does it give us? 90 equals, now we have a s plus 10, b s plus 100, which by our usual maneuvering, we can set s equal to some strategic values here, such as negative 100, which gives us that 90 equals, looks like negative 90a. That one will disappear, so then a must be negative 1. And by the same token, if we set s equal to negative 10, then we get 90 equals b times, 90 equals 90b. So b equals 1. Alright, so then taking that and putting it into our original expression here, what did we have? It will now be I equals, so now we're going to have that 1 minus e to the negative s. Don't worry, we are going to be dealing with that shortly. And now what do we have? We had 1 for the b, so I'll just put that one first, so it saves me the awkwardness of subtraction as my first term. So s plus 100 minus 1 over s plus 10. 1 over s plus 10 minus 1 over s plus 100. What I mean to say. Okay, now what we can do is just distribute this to throughout, and we'll just FOIL it all out and see where that gets us. So that's going to be 1 times the first, so it's going to be 1 over s plus 10 minus 1 over s plus 100. Okay, now for the next part, what do we have? We have minus e to the negative s times 1 over s plus 10, and then we have plus e to the negative s times 1 over s plus 100. And if we were at this point to consult with any handy table of Laplace transforms, we would find things like this as some of the primary entries in them. In particular, this is just going to, so this right here, if we take it backwards and we make it little I, so we do the inverse Laplace transform, this one and this one are both canonical. They belong exactly squarely in the midst of any Laplace transform table. These are e to the at, where a here would be negative 10 and a here would be negative 100. So there we have that part. Now these other ones are basically the same thing, but with an extra factor of e to the negative s. So here we'll put in a little note. Remember that little formula from last section where where we saw that the Laplace transform of UA of t times f of t minus a, where that is exactly something of this form, e to the negative as, and then times capital F of s. So that's what we've got here. We've got a known Laplace transform times something of the form e to the negative as, where a here would be 1. And so what does that mean? That means that this will be u sub 1 of t times e. So it's just going to be this exact thing, but where we used to have a t, we should now have a t minus a, so t minus 1. Okay, well, so be it. And then what happens next? We have plus u sub 1 again of t, and then e to the negative 100 t minus 1. All right. Well, that's what it is. Interesting stuff. Let's, though, try to get a look at this once again using our favorite graphical tool, Desmos, and see what's going on, and see if we can try to make any sense out of it from the perspective of electricity and circuits. And if we can't, then we'll try to make sense out of it by the next best thing using the electrical mechanical analogy, and try to understand it in terms of a spring, which is something that is always a little bit easier to try to wrap one's head around, I think, than the electrical thing is, at least for me, who I am not any expert by any means on electrical matters. And so, as usual, when I have trouble trying to figure out what's going on the electrical side of things, I try to visualize it instead in terms of the spring. So let's see how that. All right, here we are, and we want to try to model this this little circuit visually. So first things first, we always need to start any of these things by defining the unit step function in Desmos. So once again, you just put the condition first, then the formula, so there's a colon separating them, then you put in the next formula after a comma. So t greater than or equal to 0, 1. Okay, so there's the unit step function. All right, so first off, there was the electromotive force that we had in this problem, which was E of t equals, and then here this just happens to be 90 times U of t. And I guess it's not liking that, so I'll just do capital E. So it will accept it. Otherwise, it reserves E specifically for our old friend, the function named after Euler. So there it is. So this is the voltage that is initially 0, and then the switch is closed, and so the voltage is it starts being applied to the circuit, and there we have it. Okay, now let's draw the graph of our actual function for the current that we found. So I of t is equal to e to the negative, e to the negative 10t. And on this, we should actually just go ahead and stipulate that we are only interested in t from 0 on. So t greater than or equal to 0. Because otherwise we get distracted by all the ones that are on the negative side of things, and those ones are not, in fact, those ones are not in fact actually applicable here. So we have this minus e to the negative 100t. And then we'll zoom in a bit on that and see exactly what we got going on here. All right. And then there's the same thing, but times the unit step function and negative. So u t minus 1 e to the negative 10. Now it's t minus 1. And then plus, and now it's u t minus 1. Oh, sorry, now it's minus again. Minus t minus 1 e to the negative 100 t minus 1. All right, that is our formula, I believe. Oh, sorry, this, so I've got, I think, the signs backwards. This one is supposed to be minus, and this one is supposed to be plus. Okay, now let's look at things. All right, so first off, what's going on at first? So at first, as you can see, the current starts off being 0, but then immediately, as soon as the switch is flipped, then what happens is the current spikes way up, or not way up, but up, and then actually the current then levels off, or sorry, it goes back down to 0. Now that might be a little bit hard to understand exactly, but remember that we're talking about the current on this. It might make a little bit more sense if we were to look at a graph of the charge. But anyway, so this is what happens, and then it levels off. And so basically this is the circuit essentially stabilizing after being hooked up to the battery. And then and then what happens is oh, sorry. So our electromotive force was equal to 90 times, and then this is actually supposed to be 1 minus. Let's say 1 minus u of t minus 1. Okay, so sorry about that. It's misreading the thing. So if we look at the actual voltage here, it is, so essentially it gets turned on and then turned off. And if you wanted, you can make it make a little bit more sense by putting it at that. So it's essentially just on for the 1 second. For the 1 second, the switch is closed and the circuit is hooked up to the battery. Okay, so that's the electromotive force. So that's the 1 second of it being hooked up to the battery. And then when you look down here, what we see is actually the current spikes up, and then it levels off, and then the circuit is opened again, and so it's now cut off from the batteries effectively. And what we have here now is induction. So now the current, in a way, almost like splashes back. So it's been building up in the inductor, which is kind of like almost like its own little battery, and then it spills back out in the opposite direction, and that's why it's negative. Now, once again, I don't find circuits particularly easy to understand, but if there is one direction that's easier to understand, it's not current, it is charge. So here's how we can actually do the charge. So remember that the current is the derivative of the charge, which means that the charge is the antiderivative of the current. Now, it turns out that Desmos is actually perfectly capable of calculating numerical integrals of functions. And in particular here, I'm just going to have Q be the integral from 0 to t of our I of t. And what's its problem here? All right, well then, x. I'm not sure what its issue is. I thought that that was okay. Okay. Oh, okay. Wait. Sorry. Nope. I just made a classic blunder. The classic blunder here of using the same variable for both parts of the integral here. Okay. So there we go. That's better. So Q of x is the integral from 0 to x of I of t with respect to t. So okay, so here we have now essentially the charge. And there it goes. There it goes. Now it's giving us a nice, reasonable answer. So the charge. So it takes a little bit for Desmos to generate these, but what we've got here is the charge. So we hook it up to the battery effectively when we close the circuit, and then the charge builds up, and then at 1 second we open the circuit back up, so it's cut off from the battery, and the charge goes back down. And again, if we are trying to think of this in terms of a spring, imagine that we are effectively pushing the spring out at a steady rate. So we can think of the charge as being the position of the spring. We're pushing the spring out at a steady rate, and so it stretches out and out and out and out and out, and then reaches basically the maximum that it's going to be distended, and then after 1 second we release it. So we apply like a constant pressure to it, and it stretches out and out and out. We release it, and it just kind of it just goes back. It's basically like a sort of like an elastic deformation. This is not a very springy spring. It has it's very, very, very damped. It's way over damped, which makes it actually more like we are sort of we're just doing essentially like an elastic deformation here. So we're just kind of pushing into some clay, and then it gradually springs back. And so that is what we can see here. And Desmos is not very quick at sketching these functions that are defined by means of an integral, but gradually it can seal the deal if you are careful in the way you name its variables. As always, Desmos is particularly sensitive to the letters that are used in its definition, and you can't use the same variable, just as in regular math, for the inner part of an integral and the outer part. But if you want to do a graph of numerically computed antiderivatives, this is how you can do it. It's not a very fast process, but it does eventually produce a graph. All right. Well, that's going to do it for this section. So thank you for joining me for this edition of Circuits, Springs, and What They Have in Common on this episode of Math 256. I'll see you next time. Till then, bye.